Okay, good afternoon. I'm Evelyn Lance. It's May 27th, and it's Memorial Day weekend. And I want to start with a very brief little tale. It might be called The Tale of Two Presidents, otherwise called Trump and Martin Luther King, and Obama and I Have a Drone. A playwright could not have staged it better. While Donald Trump was giving the Pope a book with Martin Luther King's writings, Barack Obama was in Berlin publicly defending his targeted assassination program. I have a dream versus I have a drone. Indeed, during the question and answer session at the Berlin rally, May 24th, Obama was asked by a student how he, as a Nobel Peace Prize winner, could defend his policy of causing hundreds of civilian casualties with the use of drones. Obama answered, "How do you defend your country from things like those we saw in Manchester or Berlin or Paris or Nice?" I guess that's how he says Nice. Sometimes my choices led to the death of civilians because there were mistakes. But drones as such are not the problem. The problem is war. Now, in a more profound and truthful sense, this is actually a tale of two LaRouches, Lyndon LaRouche and Helga LaRouche. And as people know, Helga LaRouche was at the Belt and Road Forum in Beijing, China, on the 14th and 15th of April. And of May, May, one of those months. And there's been quite a bit of coverage internationally. Unfortunately, there has not been quite a bit of coverage in the United States, but there has been quite a bit of coverage internationally. And probably the one that summed up the views of numbers of people around the world these days was a short May 16th editorial statement in something called the AfricaAgenda.net. It's entitled "The World's Most Incredible Woman." It says, "Thank you, Mrs. Zepp LaRouche. Thank you for devoting your lifetime to realizing a vision that you have to create a different kind of world to the one we all live in. Your dream is becoming a reality. You are one incredible soul. You said at a conference that I once went to that as a young woman you traveled in the world and were so horrified to see the poverty and desperation that is life for so many people. That was your catalyst, your mission to change this world and make it a better place. In opposition to your vision of humanity and our incredible potential is the most parasitic, satanic, soulless empire that this world has ever lived under. And you, Mrs. Helga-Zepp LaRouche, have nearly defeated them." That was what they had to say, and it was called the AfricaAgenda.net. It's an online publication. Now, Helga is still in China, at least as far as I know. She was yesterday, speaking in Nanjing, China, to the largest publishing company in China, the Phoenix Press Publishing Group. She also had an article which was covered in the China Investment magazine, which was published in both English and in Chinese. And at the meeting of several hundred people at the Phoenix Publishing Group, you had a discussion both by Helga LaRouche of the Belt and Road, but also of the fight over decades by Lyndon and Helga LaRouche for a just new economic order. Then it was detailed further by Bill Jones of EIR, and then a professor who is a professor of military strategy in China also joined the discussion, and he also discussed the role of the LaRouches as being seminal in the Belt and Road policy. Now, think for a minute. Imagine such a meeting being held at the largest publishing house in America. That's what just occurred in China, and that's the gap we still have to close between what's going on in the United States and what's going on in China. But while Helga and the Chinese were engaged in creating the future, the G7 was engaged in basically putting an end to a group called the Group of Seven. They had a national leaders meeting in Italy where there was absolute conflict between President Trump and the rest of the leaders there, although with he got some help from the Japanese Prime Minister. But it was so contentious that there was a general agreement that the final accord was not going to mention free trade, was not going to mention climate change, was not going to mention the refugee policy. And interestingly, President Trump was actually fighting for a policy almost identical to what President Putin of Russia called for a year and a half ago. That what is needed is an alliance of nations to fight terrorism. And we're not quite there yet. And to me, one of the signs that, you know, of what happened at that meeting was that British Prime Minister Theresa May left after the first day of a 2-day summit. So that gives you an idea. Now, there's another summit coming up in July of the Group of 20, which should, one would think, would be a better venue for discussing some real ideas, because it involves different countries that would want to discuss real ideas. Unfortunately, it is being held in Germany and chaired by Germany, and they're going to be pushing an agenda for green, environmental, no-growth policies, which will not get anywhere, but it means nothing else will be accomplished either. On the other hand, you had the Belt and Road Summit in May. Now, next week in St. Petersburg is called the St. Petersburg International Economic Forum. That's June 1st through 3rd. And then on the 8th and 9th of June, in Kazakhstan will be what's called the Shanghai Cooperation Organization, which was originally begun by China, Russia, and some of the Central Asian countries. And India and Pakistan will, there will be a discussion of them joining. Now, think about one of the most important geopolitical splits that the British have played between India and Pakistan. So to have them working together in the same organization with Russia and China will be a real step forward for the human race. Meanwhile, the question becomes, what will the United States do? Will the United States join this and actively, work with it? Because if we do, then the countries of Europe will join as well. Even with the United States only having one toe in so far, because Trump did send a delegation to the Belt and Road Conference, a fairly high-level one. But even so, in Eastern and Central Europe, you have the Czech Republic, who sent their president to the Belt and Road, Serbia, Hungary, and even in Western Europe, there's movement by Italy and Greece in the direction of the policy of the Belt and Road, since they have no future with the European Union and the transatlantic system. Meanwhile, I won't try and go through what is occurring in Libya because it's very chaotic, but suffice it to say that the Manchester bombers' father was a leader of the terrorist group, Libya Islamic Fighting Group, and has now been put under arrest. The brother of the bomber has been put under arrest, and there's tremendous fighting going on in Libya between 3 different factions. It's not clear exactly what is going on or who will, emerge victorious. One thing that is clear is that the terrorism in Egypt, they see as coming from Libya, as it probably is. And the Egyptians launched a bombing raid against the town of Derna, which is near the Egyptian border, to bomb some of the terrorist training camps. So we are in a world where the question now is, when President Trump comes back to the U.S., which I believe is today or tomorrow.
It's today.
Today.
Mm-hmm.
Can we have the kind of movement required to get him moving on the policy in the U.S. of Glass-Steagall and LaRouche's 4 laws, so that the U.S. becomes part of this? Will he take on Wall Street, and fight? And I would recommend a couple of videos on the website if people have not watched them yet. One is called Mr. I Don't Do Evidence, Brennan, and the mass media. And it's about a 5-minute clip. It's very good.
Mr. What evidence?
I don't do evidence.
I just lied.
Yeah, right, exactly. He was putting out all this stuff about, the Russian connection of the Trump administration. And they asked him for evidence, and he said, I don't do evidence. And what the videotape does is shows a bunch of headlines from U.S. papers all about how he had presented evidence on, or how he had presented proof of the Russia connection. And then you're shown clips of the actual hearing with questions from Congressman to Brennan. And the best he can do, I don't do evidence. So that's one. And the other was just put up today is Senator Richard Black. It's an 8-minute video on the question of chemical weapons in Syria, which completely debunks any argument that the Syrian government, was responsible. So those are very good and to circulate. And then we mentioned this last week, but to mention it again, out in the hall are these petitions. Congress, suck it up and move on. It's time to rebuild the country. And people should be taking those and circulating them and getting signatures. Because if you sign it, that's a good thing. But if you get another 10 or 20 people to sign it, that's how it's going to be effective. So with that, I will turn the program over to Joel DeJean, who's going to give an exciting discussion of the glass universe.
You need a marker, Joel?
Yeah.
You got it there.
All right. So there was a book review that came out recently with the provocative title, Calculating Women. And the book's title, it wasn't Calculating Women, it was actually a review of 3 books that were published in the last year by 3 different women. 3 books on women in science. And one of them was Hidden Figures, about the role of what we call human computers, mostly African-American women computers who worked at the Langley Research Center. Another one, there was a very good movie of that book, which hopefully you've seen, called Hidden Figures. Another one was the Rise of the Rocket Girls, about the women in Pasadena Jet Propulsion Lab in California, their role. And the third one was called the Glass Universe. Now, it's not about the glass ceiling in astronomy, but it was written by a woman called Deva Sobel, and she begins the book with a banquet in 1882. And at the banquet, it's hosted by an astronomer, a chemist, a professor named Henry Draper. He's 46, and he was the son of a famous doctor. His wife was the daughter of a very famous railroad magnate at the time, Palmer, and she's very, very wealthy. And at the banquet, there are about 40 people, astronomers, scientists. And at the banquet, you have a 35-year-old Thomas Edison. And the banquet, the author makes a note that the banquet was lit by electric lights. And she says that Henry Draper was proud of the fact that he was able to light his room better than the President of the United States at the time, Chester Arthur. So at the banquet, Henry Draper falls ill. And he had been an officer in the Union Army, and he had recently returned from a trip out to the Rockies where he was taking some astronomical observations, and his crew had been caught above the timberline in a snowstorm. So he got ill, and about a week after the banquet, he dies of pneumonia.
What?
Pneumonia, severe pneumonia. Now his wife is devastated, Anna Draper, and they had no children, so she dedicates herself to continuing the astronomical work of her husband. Her husband had been a professor at New York University. He had retired from teaching at New York University. He was going to expand his observatory in a place called Hastings up on the Hudson, about an hour north of New York City. So she dedicated herself to continuing his work. Now, she had collaborated with him for 50 years, writing down the measurements, doing calculations. Now, also at the dinner was the head of the Harvard Observatory, a man by the name of Edward Pickering. And Pickering, after Henry Draper dies, writes to Anna Draper and requests that she send him what was known as photographic plates that her husband had taken. Because at the time in the 1880s, you had four major breakthroughs in science. You had the telescope had been around for 250 years, but the use of photography in telescopic observations was a new science, photometry they call it. Also, the use of the spectroscope or spectroscopy was being used to break the light coming from the stars into their spectrum. And you had developments in chemistry, and Mendeleev was developing his tables. The chemistry industry was being built up in Europe and the United States. And also electricity with Edison and the electric light and electric motors. So what Draper had done is, besides just looking through the eyepiece, he had begun using photographic plates to take long-term exposures of the stars and then look at the plates with a microscope to observe the stars that way. Now, his plates were about 1 inch square. So Anna Draper sends the plates to Pickering at Harvard. Now, Henry Draper also had just begun using prisms to do spectral analysis of the starlight. And so she sends the plates to Pickering. And Pickering, now the Harvard Observatory was about 40 years old at the time. It started in 1839. And it was not directly part of Harvard. It was a research arm, but the research involved the director, and his salary had to pay for all the assistants. So a lot of the calculations were done by either the wives or the daughters or the relatives of the astronomer. Now, I want to give you an idea of what type of equipment they were using at the time. So, Mike, if you put up the slide of the telescope. I don't know if many of you may have had a chance to go observe the stars with Michael McCallie, a late astronomer in the Houston local. And he had a reflecting telescope where, is it up there?
Yeah.
Okay. So this was about a foot. The glass, the actual optics is about a foot diameter. And the light from the star comes through the barrel, reflects off the eyepiece or the glass into the eyepiece. So what Draper and Pickering were beginning to use is photography. Instead of looking at the star, you put the camera and you take a long exposure. And then if you adapt the prism to the camera, then you could break out the starlight. Now, Pickering, in his appeal to Anna Draper, he says that given the difficulty that you will have in recreating your husband's work, I propose that in honor of his work, you finance a catalog, what would be called the Henry Draper Catalog of the Heavens, that I will conduct at Harvard, because I have the facilities, and I can hire some of the assistants to continue your husband's work. And Anna Draper agrees to contribute about $1,000 a month to his observatory. Now, I happen to have a photographic plate, for an example of a photograph. This one talks. But if you imagine the eyepiece, where you have this photographic plate, which is a glass plate about 8 by 10 inches, so a little bigger than this, with a chemical emulsion. Now, they were initially using wet emulsion, so that every picture, you would cook up your emulsion and spread it on the glass and then take the picture. And then during the daytime, you would have your human calculators or human computers look with microscope to observe the various stars that were taken overnight. Now, Pickering had recently hired a house servant, basically a maid, to help his wife in the observatory, because they lived at the observatory with various telescopes there. Now, Anna Draper contributes some of her husband's telescopes to Harvard to continue the work. And the maid was named Wilhelmina Fleming. She had just come in from Scotland. Her brothers had emigrated from Scotland, and she had a recent marriage breakup, so she followed them there. So she was a house servant. And Pickering's wife realizes that this house servant is very interested in what's going on at the observatory. So Ed Pickering assigns her, or recruits her, as one of the human calculators, human computers, to, during the daytime, go through with a microscope and catalog the magnitude and the spectrum of the various stars on each plate. So each plate would have the time of exposure, the location, the position in the night sky, so that you would literally build up a catalog of plates. And eventually the observatory had something like 500,000 glass plates.
Oh my gosh.
With the catalog. And what they would do is that you would observe the spectrum, and then if something like a supernova would occur, you could go back to the catalog and pull out and see what the sky looked like 5 years before the supernova, a year before, a few months, and then, so you could go back and observe the night sky, both backwards and to the present. Now, what's interesting about the night sky, and how do you measure the stars? Now, I remember back in the early 80s, I was driving back from El Paso on Interstate 10, and I was driving by the McDonald Observatory out in West Texas. Now, I unfortunately never took a trip there to the observatory, but I had the T-tops off, and I looked up, and you could see thousands of stars. I'm sure if you get away from the city lights, you see in the desert or somewhere where you don't have the glare of the city lights.
You don't have any civilization.
Well, yeah. That you see thousands of these lights, but over eons, man has used the position and the movement of the stars and the planets to navigate, to create calendars. So we've been observing the stars for thousands of years. And astronomy could be called the first science, besides music, astronomy. Now, you can look at the stars as just points of light in a hemisphere. If you've ever been to a planetarium, you see all these dots on the ceiling, and it moves depending on the time of night and the season. But how do you tell how far those dots are? Because if the star is not moving, if a planet is moving, you can tell by parallax the approximate distance. But over a greater distance, it looks like the stars are fixed or permanent. And Aristotle actually believed that the heavens were fixed, that everything was permanent. And the earth was changing, so the earth was evil because it changed, and the heavens were perfect.
Wow.
So over the years, with the telescope, we're able to observe the movement of the moons of Jupiter, of the face of the moon, the contour of the moon, what was going on the surface of Mars with dust storms and things like that. But we still had no real estimate of the distance. Now, what Draper had begun and what Pickering picked up on is the use of not only photography to measure the brightness, but spectroscopy to actually break down the starlight. Now, Mike, if you put up the spectrum.
Hey, Joel, before you start that, can you tell me how long did they have to do that exposure? I mean, because the stars are moving and...
Well, that's the use of electricity. What they would build, and a lot of the telescopes, the astronomer would order the plate, the glass, and then actually grind a telescope himself or with his assistant. Then he would build the motors so that his telescope would track the stars to counteract the movement, the turning of the Earth. So the exposure would be about 2 hours typically.
Wow.
And you can either pick out individual stars or take a wide field of view. Now, is the spectrum up there?
Yeah.
Okay, so if you concentrate on what they were working with is the visible spectrum. So if you go from red is at the left, right? That's
right.
Red is at, okay, you flipped it. All right. So if you go red to green to blue, if you look at light coming from either the fluorescent lights or just daytime, it looks like it has all the colors in there. It's white. But if you use a prism to break out the colors, you see the various colors from red to blue. So what they would do is with the prism, they would break out the starlight coming from the distant stars. Now, earlier in the century, in the 1816 thereabouts, a German optics maker by the name of Joseph Fraunhofer used a telescope and a prism to look at the sun. Now, don't do this at home. You don't want to look at the sun, but he projected onto a plate, not a photographic plate, but he broke out the light coming from the sun, and he observed that it was not a continuous spectrum, that you had these lines, these vertical lines throughout the spectrum. Now, can you show the hydrogen?
No, we haven't gotten to that yet.
All right, can you?
Well, first off, we got the continuous versus the emission lines and absorption lines.
Okay, go to that.
So we can explain that.
All right, so if you look at light is a electromagnetic wave. So red light, if you look at the wavelength, is about 700 billionths of a meter. And if you go up the scale, blue, the wavelength is about 400 nanometers. So that if you have a mechanism so that you can tell where these lines are, you can tell what wavelength you have these, what they call Fraunhofer lines. So what the people like Miss Fleming were doing is using the telescope and then the microscope and plates. They would catalog, and the stars on the plate would be about a centimeter, real tiny specks there. But they would catalog the spectral analysis of each individual star and record its position and time of exposure, etc. Now, if you look also, if you've ever taken a chemistry class, even high school chemistry, where you take an element and you heat it with what's called a Bunsen burner. You heat it, you'll have emission lines that are different depending on your elements. So each element has its own, what's called a fingerprint, called the Fraunhofer lines. So you have the absorption lines and the emission lines, which for each element are in the same position. Now, in the early 20th century, using the quantum theory, they were able to explain that. I'll go into that a little later. But go to the next one. You have the emissions and the.
Yeah. So this is hydrogen emission.
Okay, so what they discovered using this spectroscopy is it was said that a chemist looking at the stars in the distance could extend his arm to the stars. And one element in particular, if you could go to helium. Now, helium was not discovered on Earth, even though you can get it at the store for your birthday parties. But
They have something.
did we have some last night?
Yeah, very good. Yeah.
But they were looking back in the mid 1860s. They looked at the stars, our star, the sun, and they saw these lines that were not the same as the hydrogen lines. Now, they assumed, this is the initial assumption, is that the sun was just like the Earth, had the same number of elements, silicon, oxygen, iron, but it was just hotter. And they had no explanation of what produced the heat. So looking at the sun spectrum, they were able to break out what became the helium lines. And they named that element Helios after the god of the sun, Helios. And it was after its discovery in the sun spectrum that they were able to look at the spectrum of a radioactive element like uranium that would emit, they basically emit the nucleus of helium. And they were able to see that the fingerprint of that emission was exactly what you saw when you looked at the sun. So they were able to discover helium on Earth after it was discovered in the sun. Now, throughout the 1890s, they're taking literally hundreds of photographic shots a night. Now, it wasn't just at Harvard or Cambridge in Massachusetts. What Pickering does is he sends his younger brother, who had just graduated from MIT, William Pickering, out to the West Coast to scout out other observation areas so that you could both be on a mountaintop above most of the atmosphere at a different location than Cambridge, Massachusetts. So he looks up and down the California coast, eventually goes through what became known as Mount Wilson, and then he goes south to Peru, because in the northern hemisphere you get one set of stars, in the southern hemisphere you get a whole different set of stars. So he actually built up an observatory in Peru where they would take photographic plates, ship them by boat to Cambridge, to Harvard, where the people like Miss Fleming would examine the plates, so you could have a map, a catalog of not only the northern hemisphere, but also the southern hemisphere. Now, at this point, he has a handful of these assistants, these human computers. With the money from Anna Draper, he's able to hire about 20 computers. Now, the hiring, they were paid about 25 cents an hour. So they were relatively low-cost help. But what happened is that there was so much of a demand. Now, at this time, 1890s, there are a lot of women's colleges that are developed, like Wesley, where Hillary just spoke at yesterday. But you had Radcliffe, Vassar College, where they were educating women to basically be teachers, basically be math teachers. But a handful were educated to be physicists, astronomers. Now, what they found is that a lot of candidates would apply to be human computers at the Harvard Observatory for free. And now, at this point, Pickering appoints Wilhelmina Fleming as the curator of photography. So she's in charge of hiring. And she says that she would not take people on for free because she would rather have somebody who gets paid than just working for free. But there was a real hunger for people to fill these positions. Now, 2 new recruits are added on, college graduates. One is Anna Jump Cannon, and another one you've heard of before, Henrietta Leavitt. And there was a play that Geisha and Ian wrote a review on Leavitt. What was the title of that play?
Mrs. Leavitt Stars.
Mrs. Leavitt Stars. So they're assigned different parts of the sky, and Miss Fleming had discovered hundreds of what's called variable stars. Because what's interesting in the night sky is not what stays the same, but what is changing, either position or luminosity or brightness. Now, at this point, if you were in the Harvard Observatory, you would have one classification of brightness. If you were in Europe, in Berlin or Paris or Moscow, you would have a different classification of brightness. So that in the late 1890s, the Harvard Observatory, through their classification of hundreds of glass plates, comes up with a classification of magnitude of stars. And it's based on the brightest star to the dimmest. And I'll just go through. This is the classification. So O type star with the brightest. Now, there was a mnemonic to remember that classification. And oh, be a fine girl, kiss me. And I think it was Anna Cannon. And they would add classifications, because as the telescopes got more powerful, you could see dimmer and dimmer stars. So they would add to the classification. So they added the R and N after M. Our star, the sun, is G classification. So when they added RM, it said, oh, be a fine girl and kiss me right now. So you had a standard of classification. Now, in the early 19th century, you had a lot of visitors and collaborators coming to Harvard to both look at the plates and collaborate with Pickering. And they set up what's become the American Association of Astronomy. And the author goes through a trip that was taken in 1910 by Pickering and these foreign astronomers. They come first, they meet at Harvard, they take the train to Chicago, and during the train trip, they're discussing and collaborating and just figuring out what would be the accepted catalog or classification of stars. They pick up additional astronomers in Chicago, they go to Arizona, and then they end up at Mount Wilson. And they eventually set up the International Astronomical Union. Now, at this point, Henrietta Leavitt is assigned to look at the plates coming from South America, coming from Peru. And she looks in particular at what's known as the Magellanic Cloud. And she discovers thousands of variable stars. And she comes up with a system that says that the brightness of the star is related to the period of the star. So since they had thousands of glass plates that covered thousands of observations, they could make a light curve of each star, that it would be bright a certain time of the year. 30 days later, it'd be dim back to, say, like an M classification, then go back up. And what she determined is that there was a relationship between the brightness of the star in its period. The longer the period, the brighter the star. And she was looking at the Magellanic Cloud. And at this time, all of these clouds were assumed to be in the galaxy, in the Milky Way, because it was assumed that all the stars in the universe were contained in the Milky Way. So she figured out that if looking at this cloud, that all of these stars must be in the same relative distance from the observatory, so that if I can estimate the brightness of the star and compare it to the other stars, and then look at another section of the sky, and if I see a star with the same brightness, then that star must be the same distance to Earth as the one in the Magellanic Cloud. And using the idea that if you have a standard candle, say if I have a 100-watt light bulb, and I have a certain brightness from that, and I move that light bulb back, say, 4 feet away from where I take the initial brightness. Now, using the inverse square law, if say you have a certain brightness at 1 feet, if you move it back to 2 feet, then the brightness will be 1/4. So you could use that brightness as your yardstick, as your measuring stick, to determine the distance to that star. Now, another astronomer who's up and coming named Shapley, who eventually becomes the director of the Harvard Observatory, he uses Henrietta's law. It becomes eventually, it's known as Leavitt's law. But he uses that distance marker to look at globular clusters around the Milky Way. And using the estimate of the distance, he comes up with an estimate distance to the globular clusters of something like 300,000 light years, which initially, that was unbelievable, the distance. And looking at the distribution of clusters, he determines that the Earth is not at the center of the galaxy, but that the Earth is about halfway towards away from the center. So that the Earth is no longer the center. Not only is the Earth no longer the center of the solar system is not the center of the galaxy. And this causes quite a commotion. But other astronomers using Leavitt's law look at the various clusters, and there's a great debate that breaks out. It says that, are these clusters in the galaxy, or are they what they call island galaxies or island universes? And eventually, you've probably heard of Hubble. He uses Leavitt's law to determine that not only are the galaxies outside the Milky Way, but they are moving away from us at a certain speed. Now, throughout the 1914, 1913, you have additional meetings of astronomers, and Miss Fleming is invited to various of these meetings. Now, unfortunately, she had a sickness, and she dies of cancer at the age of early 50s. So she dies in 1921.
We're talking about Fleming or Leavitt?
Well, Fleming dies in 1911, and Leavitt dies in 1921. And so Anna Cannon is put in the position of the curator of photography for the Harvard Observatory. Now, at this point, she's not a member of the faculty of Harvard, and she's not considered a professor or even an astronomer. But Pickering, besides hiring all of these human computers, he also encourages them to publish, and he publishes a catalog called the Henry Draper Catalog of all the results of all of their measurements going back over the last 20, 30 years. And he encourages people like Fleming when she was alive, and Leavitt and Cannon, to publish in their own name. Now, in the early 20s, you had another computer who was heavily represented in the book, called Cecilia Payne. And she was born in 1900. And she was studying in Cambridge, England, in British. And she attends a lecture given by a well-known British astronomer called Arthur Eddington. And Eddington is famous for being the one who verified Einstein's general relativity in 1919 by observing light bending while observing a total eclipse of the sun in 1919. Now, Miss Payne attends a lecture given by Eddington and decides to become an astronomer. Now, not only is she an astronomer, but she has also studied atomic physics. So what she does is she goes back into the catalog and takes another survey of all the glass plates going back to the early 1890s. And she is not only looking at the spectra, but now with her knowledge and background in atomic physics, is able to say that the reason why you have these Fraunhofer lines is because as the sun or as the star heats up, the elements of the star's atmosphere will excite the electrons, and the electrons will move into certain locations. And because of that, you can determine the exact ratio of elements in the star's atmosphere. And she does a survey, and she actually uses this survey as her doctoral thesis. And she becomes the first doctor of astronomy who's awarded that degree by Ratliff, which was associated with Harvard. And she eventually becomes the head of the basically the Harvard Observatory, not the official head, but the head of taking the catalog, publishing, things like that. Now, if you go to the next slide, like iron.
Yeah.
Okay, so again, it was assumed that the stars were made up of the same ratio of elements as the Earth. And you have iron and calcium, but what Ms. Payne discovers is that if you look carefully at the spectral lines, the abundance of hydrogen in the stars is 1,000,000 times more than the abundance of hydrogen on Earth relative to the other elements. Now, she initially discounts this, says that this must be wrong because it was assumed that the distribution of elements in the stars was just like Earth. Now, she persists in this, and eventually her theory is borne out, and it's shown that the stars are not made of just earthly elements, but the abundance of hydrogen and helium in the stars distributed throughout the universe is millions of times more than the other elements. And eventually in the mid-50s, it's discovered what is powering these various suns, what is driving the sun's energy, which is fusion. But that's discovered, or that's confirmed later on in the century. Now, at this time, you have literally millions of photographic plates at the Harvard Observatory, and what Pickering feared the most is if there had been a fire at the observatory. So he spends a tremendous amount of time raising funds so that the plates could be stored in brick buildings. And he eventually builds not only additional brick buildings, but he puts in a sprinkler system so that if there's any type of fire, the fire could be suppressed. Now, unfortunately, I think it was last year, the sprinkler system developed a malfunction. And the plates, thousands of plates were basically covered up by water. And the fear is that you would have mold and moss growing on the plates. So you have all these star patterns sprinkled with mold, and you would know what's what. So what they're doing now is that they're cleaning up the plates in dry rooms, and they're digitizing all of the plates so that the 100-year catalog of these plates will be accessible on the internet. Now, if you look at the way we take photography now, is instead of using emulsion in photography, they use what's called charge coupled devices, so that, like the Hubble, when the Hubble takes a picture, the Hubble in space, you don't go up there to get the plates. You transmit the data electronically, so that you have a digital record of all of the beautiful pictures you see from the Hubble. Those are all from digital photography. So that if you look back at the history of this observatory, not only did it provide a training ground for the human computers, the women calculators, but a large number of them eventually became astronomers or doctors in the various fields. And to this day, out of the 300 or so researchers at the Harvard Observatory, about a third are women. So you have this tradition going back over 100 years of women not only working in astronomy, but developing some of the techniques that allowed us to actually measure the distance of the stars. And they have refuted the idea that there's nothing new under the sun. It's one of the worst quotes or misquotes in the Bible, that there's nothing new under the sun. Not only is there new knowledge to be gained, but we now know the life cycle of the stars. So not only is there new under the sun, there are new suns. And with this knowledge, and one of the best quotes in the book is that Pickering he's getting all this money from Anna Draper, but she's losing some of her real estate holdings. So he appeals to Andrew Carnegie to help finance. And he says that the glass plates at the Harvard Observatory are like a library. And each plate is like a book of the heavens. And what is needed is readers for the books. Because you could have all of the data in the world, but if you don't have individuals who can look at the prints and figure out what the relationships are, then all of this data is useless. So now we have observatories not only all over the world, but in space. And the idea is not just limited to Earth orbit, but eventually put telescopes on Mars and eventually further out in the solar system. And eventually in the far side of the moon, because now not only can we read the spectral lines of the visible spectrum, but we can look at radio waves, X-rays, gamma rays, and eventually gravitational waves. So I highly recommend the Glass Universe as part of the series of not only the Hidden Figures, but the Rise of the Rocket Girl. It gives you an idea of what real history of science is and what's been hidden from us for too long. So I'll stop there and if there's any. Oh yeah, did you show the picture of the? This is a picture of the Harvard Observatory. Now I don't think it doesn't have the names of people, but I'm sure Cecilia Payne is there. Unfortunately, Leavitt and Fleming had passed already at this point, and even Pickering died in 1919. But you have this. At this point, I think they had 40 researchers, and 18 of them were women, either calculators or astronomers. So I think that's the last one, right?
Yeah, that's it.
All right. I should have put a picture of Hubble in there, the Hubble telescope. But that's for another.
How in terms of the scale, the original picture you showed us versus something like the McDonald Observatory of the telescopes?
Well, the original picture there was about a foot in diameter for the optics. The Hubble in space is 8 feet, but it's 8 feet above the atmosphere, so you can see much further. The McDonald Observatory, I think, is something like 100-inch. The Mount Wilson Observatory is 100, so about 9 feet. Now there are telescopes in Hawaii, Mauna Kea, that are 30 meters. Now it's not one piece of optics; it's a set of hexagon images, and it's called adaptive optics because as the light from the star comes through the atmosphere, you have the twinkling. That's because of the movement of the molecules in the atmosphere. Now, based on some technology developed by Star Wars, or the Strategic Defense Initiative, you can shoot a laser through the atmosphere and determine the turbulence. And using motors on the back of these segments, you can adapt the various segments of your telescope so that you compensate for the atmospheric turbulence. So now you have proposals to build 30-meter optical telescopes in Chile, in Hawaii, and also in South Africa.
Do they have any in Japan?
The Japanese are involved, but usually by being visiting places like Hawaii, Mauna Kea. I don't know of too many observatories in Japan. But the Chinese are building a huge, I think they finished a radio telescope. There's one, you've probably seen pictures of the one in Puerto Rico, the Arecibo radio telescope. So that if you're looking at the radio spectrum, you need a bigger telescope because your wavelength is bigger. So the one in Puerto Rico is about 1,000 feet. And the one they're building, they finished in China, is about 1,500 feet.
The aperture?
Yeah, if you look at your satellite dish, you can have dish TV, a foot. It's 1,000 feet. No, it doesn't move. It moves with the Earth, and it reflects the radio waves to a focal point where you have all the instruments above the parabolic curvature, and you could use the movement of the Earth to look at different parts of the sky.
Wonder what happened to their budget now they've gone bankrupt.
Oh, the Puerto Rico?
Yeah.
Yeah, I mean, this is, if you look at the history, I mean, part of Pickering's job was to raise money.
Yeah.
I mean, and authors, Davis Sobel, goes through how it's ironic that two of the key funders of the early part of the Harvard Observatory were both women philanthropists. Anna Draper and another one called Catherine Bruce. So they would contribute parts of their fortune to Harvard, but to the Harvard Observatory. They didn't receive money from Harvard Corporation of the university until 1950s. So you had all these private contributors to the development of things like the telegraph, but it wasn't until World War II, and she goes through some of this at the end of the book, that the two world wars cut a lot of the collaboration between the German astronomers and the British and American. After World War II, a lot of the funding became government funding, but a lot of it is spin-offs from the military. Because if you look at the radio telescopes, that didn't exist until the 1940s. And what they did is they would have a radar and they would have interference from when they blasted the radar to look at planes coming in. They would have echoes from the moon. And they figured out, well, we could use these radio waves to measure things. And then they would look out further in the galaxy, and various stars would transmit radio signals. So you could use radio waves to actually measure the stars. So a lot of the funding now is government. And with these cuts, it's crazy. And you look at what the Chinese are doing, not only are they funding Earth-bound telescopes, but they're pushing for next year to have a radio telescope on the far side of the moon.
So was it Hubble that actually made certain a breakthrough from some of the work of the of Leavitt and people who came before her in terms of the relationship of the understanding that there were other galaxies out, because before we only understood our own Milky Way galaxy, but then we started to develop the Andromeda galaxy and various other things that people didn't know were out there because of the whole distance relationship, the measuring candle.
Yes. Well, Hubble in 1924 used Leavitt's, what eventually becomes Leavitt's law. And they're actually pushing, I don't know if they've adopted it, but in 2009, there was a push by the International Astronomical Union to name this distance marker after Leavitt. But so she made a breakthrough in 1911 by doing a survey of these plates from the observatory in Peru, which looked at the Magellanic Clouds. And she was not able to continue that survey because of illness and other things, and she dies in 21. So a guy by the name of Arlo Shapley used her candle, her measuring stick, to estimate the size of the galaxy. But because of the size of the telescopes, you could see these fudge, these nebulae, like the Orion nebulae, and you assume it's just dust. But if you have a big enough telescope, you can break out the individual stars. And it was Hubble in 1924 who he actually writes to Shapley, who by that time is a director of the Harvard Observatory. And he says, I have just found these Cepheid stars, these variable stars in the Andromeda galaxy. And he says that this proves that there are other galaxies out there.
It's 1924.
That was 1924 when Hubble writes to the Harvard Observatory. And then they had conferences, and then they looked at, not only were they outside the galaxy, but they were moving. Because if your spectrum is shifted to the red, it shows that the object is moving away from you. If you look at the spectrum in the lines of hydrogen, say, and it's shifted to the blue, or the blue, then it's coming towards you. And actually, the Andromeda galaxy is coming towards us. It's coming, so it's going to collide in the next few billion years. But there's so large distances between the stars that it's thought that there won't be any collisions. There'll just be gravitational effects. So we got to stick around a couple billion years to see how that turns out.
Joel, it's not clear to me how they determined that there were other galaxies. I mean, they thought there was one galaxy. How did they determine? I mean, the distance doesn't tell you that it's a different galaxy.
Yes, it does, because if your estimate of your galaxy, eventually Shapley thought it was 300,000 light years.
Right.
And Now, just to give you an idea, I mean, this is a light year, you know, is the distance that light travels in 1 year. So in 1 second, light travels, like if I shoot a laser to the moon, you'll get to the moon in about 1.5 seconds. So light travels 180,000 miles in 1 second. So in 1 year, that light beam from a laser, if I shoot it at Mars, will get there, and depending on its position, in like 30 minutes, maybe 12 minutes, depending. In 40 minutes, you can get to the Junos. Like when the Juno spacecraft around Jupiter send a signal, it takes about 40 minutes to get to Earth. In 1 year, light will travel something like 6 trillion miles. So the galaxy was estimated to be 300,000 light years. Eventually, they factored in that there was dust in between a lot of the stars, so you had to then reduce the brightness, and so it reduced your distance. So it's thought of as now 100,000 light years across. If you look at the Andromeda galaxy and you see the standard star, and you determine the rate of its dimming and brightness, so you determine what type of star it is, and you determine your observed magnitude, you could estimate the distance, and it was estimated that the Andromeda galaxy was 1 million light years away. It's actually something like 2.5 million light years away.
Isn't the closest star is what, Alpha Centauri? I think that's
Right. Yeah. That's
what, like
4 light
4
years.
light years. So it's very, you can tell 4 light years versus like the 1 billion.
Or a million.
Billion, yeah.
Million light years. And as we've gone above the atmosphere with the Hubble, you can see they estimate light coming from 13.5 billion years ago. Now, just because we have all these plates, don't assume that we know everything. You know? They're actually looking at the center of our galaxy with radio telescopes, because you can't see the center of the galaxy because there's a lot of dust in the optical wavelengths are absorbed by the dust, so you can't see. So they're going to use a series of radio telescopes to try to take a picture of the center of the galaxy. And they think there's a large mass there of the equivalent of 4 million suns, our sun, because they can look at stars orbiting close to this black hole, and they estimate the speed of the star, and they can estimate the mass of the center. And some galaxies, they estimate that the center is 1 billion suns, 1 billion times the mass of our sun.
So these are basically the source of the gravitational field or the electromagnetic field that holds the galaxies together? Or what do they
No, it's
hold it all
gravity.
together?
Gravity holds it together.
Yeah.
And using Kepler's laws, the relationship between this cube of the distance and the square of the period, you can estimate the relationship between stars and what it's orbiting. Now they have all this, besides black holes, they have this dark matter and dark energy. So there's a lot that we don't know. So we
There's
need,
also the black hole.
yeah. So we need more Henrietta Levitts or Cecilia Paynes,
Hey, Joel,
Catherine Johnson.
Joel,
Yep.
if you were in, let's say, a classroom with kids, how would you describe what gravity is?
It's acceleration. Because if I drop something,
Yeah.
It does it come back up?
it accelerates. And if I drop, like this is heavier than this.
Right.
So which will hit first?
At the same time.
I can't tell which one. But they did this on the moon. I don't know if you saw it. You can probably see the
No.
YouTube video. I think it was Alan Shepard. And he had a hammer and a feather
Oh, yeah?
on the moon. And because it's this no air or just a few molecules. And so there's no, if you drop a feather here, it has wind resistance. But on the moon, you drop the hammer and the feather and it hit the same time. So gravity is the acceleration of body.
Actually, that was Dave Scott.
That was what?
Dave Scott.
Okay, that was.
So go ahead, you were about to explain.
Oh, but then what Einstein proved is that gravity is not just acceleration; it's the bending of the fabric of space and time. And using his general relativity. And by the way, one of the key German astronomers who in 1916 used Einstein's relativity equations to figure out that you would have something like a black hole. And he did this while he was serving on the Russian front, Eastern Front. And unfortunately, he died. He not of bullets, but of some kind of fever. So if you look at what happened in World War I, you had thousands of these college-age, high school potential geniuses who were wiped out. But what Einstein proved is that it bends, and he predicted, he forecast that if you look at light itself will bend in a gravitational field. And it was this expedition by Arthur Eddington, who, looking at a total eclipse, so you could see the light of a star behind the sun. Looking at the eclipse, Einstein had projected that the image of the star would be shifted 1.7 seconds, a real small distance, but 1.7 seconds. In the experiment that Eddington ran during this solar eclipse proved that Einstein was right.
So it was an eclipse of the, say that again, an eclipse of the,
Of the sun.
yeah.
So that if there's a star behind the sun,
Right.
now, if the Earth is in, say, the behind the sun, say, and you look at a star and you know its position, and then 6 months later, the Earth is in front of the sun, and you look at that same star, but the sun's in the way. And because of the brightness of the sun, you can't see that star. But if the moon covers the sun for a few seconds, and that star is right on the rim of the sun, then you could see, because of the eclipse, you can see that star, and you can estimate, well, is its position what it was 6 months ago, or has it moved? Because now the light from that star is coming around the sun and it's bending. Not refracting, but actually bending because of the huge mass of the sun.
So it's not like it's on the edge and it was behind, but it's just on the edge and it's bending. In other words, the light would pass by the sun like in a straight line, or the
Yeah, you would assume that the light, see, light is not affected by magnetic fields usually. But Einstein, because of his general relativity theory, he said that light will be affected by large mass. And the largest mass we had to deal with is the sun.
right.
So that if this star that you're looking at is close to the rim of the sun, when the sun is in front of the Earth.
Right, not behind the sun, but
Right.
next to, but the rays are coming next to it.
Right on the rim.
Right on the edge.
So that if you have the eclipse, then you could see the light and you can see what is the position of that star. And it actually shifts a few,
Like
1.7 arc seconds. And that's another discovery that was made by, I think it was Cannon, is that some of these variable stars are not because they're getting brighter and dimmer, but it's because it's a binary system and you have one sun coming in front of the other. So if one sun is dimming, the sun behind it. So they actually discovered a whole series of binary stars.
So today, the whole process is obviously different because of the technology, the digitalization of the images, right? I mean, is that?
Well, what they use now is instead of glass plates, they have like your camera. Like this is the camera.
Right.
Where's the film? But it also goes back to the quantum, because you have a detector that senses the photons coming in. And if there's a photon that hits the detector, it will produce an electrical signal. So that if you have a certain number of pixel elements, like your iPhone camera has like 5 million pixels. So it's an array of 5 million individual detectors. So you scan electronically so that as the light hits your detector, it paints an image. So that where it's bright, you'll have a certain voltage. Where it's dim, you'll have a certain voltage. And you change that voltage to ones and zeros. And you put different filters in front so that you can have red, green, and blue, so you can make a color image. and you just scan an array of detectors and you produce a picture. And if you just use one frame, you produce a photo. If you continually upgrade, update the scan like 30 times a second, you produce a video. So instead of using photochemistry where the light will change the chemistry on your plate or your film, you will change the output of a photon detector. And depending on the number of photons that hits, it determines brightness. So that, imagine you have an array of detectors and you're looking at an image and you just scan that image. That's how they produce a picture. And then once you have that digital picture, what you can do is you could say you can compare one picture to another, so that all you do is you're looking for the change in that picture. So that if I take a picture of the room and one person moves, and I compare a picture before they moved and after they moved, then I compare those two images and I can transmit just the amount of information of the person moving. I don't have to transmit the whole picture. That's how they compress the transmission rate of videos.
Really?
That like the zip file does.
You know, like MP3 or something.
So you said all these plates are going to be put on the internet?
Right, what they're doing since this flood, and you can imagine Pickering's nightmare was you had all these wooden buildings with the dome, and you had all these plates on their side with the envelope with the all the data, time of exposure, location, what part of the sky. So you have hundreds of thousands of these plates. And if you had a fire, the whole image would melt. So what they're doing is they're taking each plate and they're cleaning the
3:35 p.m.
any fingerprints. Although they're actually taking a picture of the plate before they clean it, because some of the people, like some of the computers, would write on the plate notes, so they want to preserve that. But once they get that image, they clean the plate and then they take a picture of the plate and digitize it so that you can preserve it. And once they do that whole catalog, then they'll have everything on the internet.
So the way everything is on the plate is a color?
Well, no, it's black and white.
Mm-hmm.
But say that if this was a picture of the night sky, so you would have dots of light depending on the brightness of each star.
Mm-hmm.
And if you look in a microscope and look at each star, you would have a spectrum.
Mm-hmm.
So it takes the light and breaks it out into red to blue, but because it's a black and white, it's just shades of gray. So that image is impressed on the photographic plate. And what people like Levitt and Cannon and these others would do is they would sit at a table like this and look at the with a microscope, look at the individual dots, and they would have a recorder, another human computer would record location, magnitude, spectral lines, and they would record that on a chart.
Oh, okay, so,
And-
so you have the plates and then you have the charts.
Right. They would publish the catalog.
Mhm.
Now, with increased magnification, you could have more information taken from the plate than you could in 1900, say.
Right.
And also, if you have something like a supernova, like they had one in 1987 in a different galaxy, huge explosion. So what you can do is you can look at the plates from 1980 and 86 and see around that supernova what star was about to explode. So you can go back in time using the plates.
When did they stop using plates?
Oh, about 1990. That's when they started using the charge coupled devices.
So they had basically 100 years worth.
Right. And it wasn't just from Harvard telescopes. It was Harvard telescopes in Peru. Because of the funding from Miss Draper and Mrs. Bruce, she would finance us to build a telescope. And Pickering would say, okay, I'm going to send this telescope to the South America, so we can take a survey of the Southern Hemisphere, so that you would have plates from both the Northern Hemisphere and the Southern Hemisphere at different times of the year. So you have this backlog of books that you can go back to and reread. And Harvard Observatory had the biggest library, so to speak. And it had the longest continuous photography.
Harvard and what?
Harvard Observatory,
Yeah.
the observatory. So they have, if you go back to 1890, they have plates that go back to 1890.
And they stopped taking plates in 1990.
Right. And so now you don't need to have a glass plate. And that's where the glass universe comes. It's glass in the universe. Not the glass. Dan thought it was a glass ceiling. Yeah. But now with you have the different, it's like your camera. Like I used to take pictures with Fuji film, Kodak film. Now you take pictures with your camera or digital camera. It's all digital. So it's the same thing in astronomy. They don't use film anymore, or they don't use plates. They save the data by taking a digital picture.
So the brighter the star was, the closer it was. So, yeah.
Well, you see, you can't tell. You can't tell that because stars have different brightness. Like if you look at our sun and compare it to a blue giant, a blue giant will have literally millions of times more brightness than our sun. So if it was right next to our sun, it would wash out the sun. But if it's trillions of miles away, it appears dimmer than the sun. But because of its distance, using what Henrietta Leavitt came up with, now you can tell how far it is by looking at surrounding stars that are your standard beacon. So now you can tell, well, this star is 1,000,000 light years away instead of, say, 10 million light years away. So just looking at the brightness doesn't tell you how far it is, unless you have a measuring stick.
And what is the measuring stick?
It's like if you had a flashlight which had a 100-watt bulb in it, and I looked at that flashlight, I can say, okay, that's 100 watts. And you move to the other room. If you double your distance from the detector, and I look at that flashlight and I measure the intensity of that light, and instead of 100 watts intensity, I measured 25 watts. If I know that you have a 100-watt flashlight, but I measure only 25 watts at the detector, then I know that you are twice the distance that you were before. And the reason is because if light is transmitted in spherical wave. Do you have a globe? Is there a Earth globe?
Yeah. Another room there.
Well, coming up.
World globe?
Yep.
Okay, so say this is the sun. Ouch, ouch. So there, say per square inch, there's a certain amount of energy coming out of the sun per square inch. Now, if this is about a foot in diameter, if I double the size of this globe, so it's now 2 feet, then the surface area will be reduced by 1/r², because the surface area of your sphere is 4 pi radius squared for any sphere. So if I double the radius, then the sphere will be 4 times the surface area. So that if it's the same amount of energy per square inch, if I double the size of the globe, then the energy per square inch will be 1/radius squared. So it's if it's, say, 1 foot and I double it to 2 feet, and it's 1/2 squared, or 1/4. So that light from a point source is spread out like a sphere. So if I'm right on the surface, it'll have a certain intensity. If I double my distance, then the intensity goes down by the square of the distance.
Because it's more diffuse.
Right, your surface area, see, if I double this globe, the surface area will be 4 times when it's 1 foot. Because the area, the surface area of the sphere is 4 pi r squared. So if your r is 1, then 4 pi r, or 1 squared, is 4 pi. So if I double this radius, so I go to my surface area of doubling the radius is 4 pi 2 squared. So the 4 pi drops out because it's the same no matter what sphere you have. So the difference between one radius of 1 and a radius of 2 is 2 squared. Or so the area of the bigger sphere is 4 times the smaller sphere. So if you have the same intensity, you should have the same light bulb. Say you have a light bulb in the center of this and you're shining the light to the surface. You have a certain amount of light hitting each square inch. So if I double the size of the sphere, the area of the sphere is 4 times what it was before. So that the same light bulb, instead of hitting 1 inch, it will hit, the intensity will be like if you hit 1/4 per square inch instead of 1 per square inch.
All right.
So that if I know what the brightness of a star is supposed to be, because not every star varies over time, but there are a handful of stars that will pulse. And because of the surveys they did with this Harvard Observatory, they determined that the duration of the pulse, the longer the duration, the brighter the star. So they developed the standard brightness model. So that if someone next to you had a 100-watt flashlight, and then you move to the back of the room twice the distance, and somebody else had a 100-watt flashlight, and I know it's 100-watt because it's blinking like 1 per second or something like that. Then I can tell your distance because the flashlight, instead of 100 watts intensity, it's only 1/4 of that. So I can tell how far you moved.
So it's the pulsating stars that become your measuring them?
Right. Because not every star doesn't pulse. Only certain stars pulse. And because of the survey they did with these plates, they looked at certain nebulae and they picked out, oh, here's a pulsing star. And you can't just look at it with a telescope one night and say that's the intensity. You have to have a monthly, yearly survey. So once you determine that that's your standard, then if you look at another cluster, another nebulae, and you see a star that's pulsing at a certain rate, you know how bright it's supposed to be. If it's dimmer than what you expect, then it means it's further out. That's because the light from that star has to cover more surface, because as it's going out, it's expanding.
Yeah, right.
Astronomy is really a multi-generational science.
Oh, yeah. Because it's the oldest science, because if you think about the navigators, you don't need to know the distance of Polaris to say that Polaris is the North Star. But 2,000 years ago, there was a different star that was the center of the rotation. So if you know the pattern that you're supposed to see at different times of the year, you can use that to navigate across the oceans. And there's one irony in that there were a protest in Hawaii, Mauna Kea, because the original peoples, not the original Hawaiians, consider the mountain Mauna Kea their god, or a holy site. So they don't want these observatories on their holy site. But the irony is the only way they got to Hawaii, their ancestors, because they used the star charts. Because if you're going, is there a Pacific Ocean here, or is there?
Right there.
But yeah, if you're going across the Pacific,
You got it right there.
you got no landmarker. So how do you tell where that little island is unless you know where the stars are? You can use them to figure out your latitude. So it's the oldest science. But if you look at the spectrum again, what we can see is based on the output of our sun, which is mostly in the red, green, blue area of the spectrum. But if you look at the whole electromagnetic spectrum, you got radio. And before 1880, we didn't even know there was a radio wave. Nobody knew what radio waves were. And before 1896, we didn't know what X-rays were. I mean, that's why they call it X, because it was unknown. X-ray. But you have this whole spectrum that we can't see. But because we figured out some principles of the universe, we can use that to extend our range so that we can see radio waves from billions of galaxies. And we can use that to measure the stars even further than we could 100 years ago.
I'm sure people still have jillions of questions, Joel, but I think we should let them ask you
Yeah.
individually.
Thank you
Thank
so
you
much.
very much.
All right, it's all in here. It's all in the black book.